everyone, welcome back to Learning at 11th Hour. So today's video is going to be about maximum power transfer theorem. We can discuss this theorem under four separate cases. Today's video, we are going to look at case 1 alone. In the upcoming videos, I'll talk about the rest of the cases. So let's go into the maximum power transfer theorem. The first case is a circuit which is purely resistive and has a variable load which is a resistive load again. So, in short, the entire circuit is going to be made up of resistances and the source. Now, we've already come across a lot of such circuits, and if it's a linear bilateral network, then we can actually represent that circuit as a Thevenin's equivalent circuit connected to the load. So, that is what we are going to discuss in the first case. So, this is my circuit. This thing that I've represented with a voltage source and the resistance Rs, this represents the entire linear network because I can actually boil down that entire network using the Thevenin's theorem into the Thevenin's equivalent circuit. So to say, this Rs is nothing but my Thevenin's resistance, and this V is nothing but the Thevenin's voltage. And this is RL, which is connected across the output terminals. Now, the maximum power transfer theorem says that the source will transfer maximum power to the load if the source resistance and the load resistance are the same. In the sense, in this case, Rs should be equal to RL. In that case, maximum power will be transferred from the source to the load. Now, how do I establish this? So, to do that, we know that the current through this network is I and can be given as I is equal to V divided by Rs plus RL. Then what is power? Power is I square into RL. This is the power dissipated at the load. So I can replace the value of I over here. I will get V square divided by Rs plus RL the whole square into RL. Now, if I want to obtain the maximum power, now power is going to be like a bell curve, for example. And if I am going to differentiate at all of these points, then I'll get some value for the slope. But the slope over here is going to be 0. So at this maximum point, where I can call this as, say, P max, when I differentiate it with respect to the load resistance, the slope is going to be 0. So dou P divided by dou RL is going to be equal to 0. So this is how we can find maxima. Even for minima, the criteria remains the same. When we double differentiate it, we can find out whether it is a maxima or a minima. If it's a maxima, the result of double differentiation would be a minus sign and or a negative value. And if it's a positive value, then we can conclude that this point is going to be a minima. So in this case, when we double differentiate, we will obtain a positive value, meaning that this is going to be a maximum value or the maxima or maximum power. So to obtain the condition that is required so that maximum power transfer occurs, we need to differentiate the power with respect to the variable load resistance RL and equate it to 0. When we do that, so we just basically have to differentiate this expression with respect to RL. So when we do that, we will get Rs minus RL and Rs plus RL as two factors when we differentiate it to with respect to RL and equate it to 0. Now Rs equal to minus RL will not be a valid expression because we can't have negative resistance. So the only factor which would be valid is Rs is equal to RL. So you can actually differentiate this with respect to RL and see that you would get this result. So we can say that when the load resistance is equal to the source resistance or the resistance of the entire linear network, which also can be called as the Thevenin's resistance, then maximum power transfer will occur. Then what is the value of the maximum power which will be transferred for a purely resistive network? So if I am able to replace the value of RL with RS in this case, I will get V square divided by Rs plus Rs into Rs. And here I'll have a whole square. So here what I have is V square divided by 2 square, which is 4, rs square, and the rs in the numerator will cancel, so only rs will remain. And rs is nothing but the Thevenin's resistance. So I can even replace s with th, and I can say that it is going to be rth instead of rs. So this is my maximum power. So let's look at this example problem. In this problem, we need to compute the value of the load resistance such that it is able to draw maximum power from this circuit. So in this circuit, there is a current dependent current source also. Now, just as we've discussed uh, a few minutes back, we know that the maximum power from this linear network will be delivered to the load if the load resistance is equal to the Thevenin's equivalent resistance, or the value of this entire linear network's resistance. So when these two are equal, in that case, maximum power will be delivered from this linear network into this load. So if we are just able to compute RTH, then our problem is resolved. So in order to compute RTH, what we need to do is we need to first identify the output terminals and then remove the load, right? So A and B are my output terminals, and if I'm able to remove this load, I'll keep it as open circuit. Now I need to compute the value of RAB looking in from the terminals AB. Next, we need to kill the sources. So here we have to retain the dependent sources and remove the independent source. So let me short circuit the voltage source over here. So then I'm just going to join this. Since this is a dependent source, we need to use the test source method. So in order to use the test source method, we need to connect a test source across the output terminals. Let me connect a 1 volt voltage source over here. Now, the resistance of this circuit would be the voltage across AB divided by the current I, because after all, V is equal to IR. If I need to find out IR, RAB, then RAB can be written as V by I. The value of V over here is 1 volt. So we need to find out the value of I for this entire circuit. To do that, first let us understand what really this I1 is. Now, as the question says, I1 is the current through this 40 ohms. And suppose I say this is I2. Now, we can apply KCL at this node, because after all, this is nothing but node A only. No other elements are connected over here. So if we apply KCL at this particular node or this node, we'll be able to find out the value of I. Here, I is entering node A, so plus I, and zero point 0.5 I1 is also entering node A, so it's plus zero point 0.5 I1. I1 and I2 are leaving leaving node A, so minus I1 minus I2 is equal to 0. So this is my KCL equation applied at node A. Now, what is the value of I1? We know that the voltage across the terminal AB, which is nothing but this, or I can say this is also AB, because there are no elements connected over here. So all of these are parallel to each other, right? So the voltage across all of these elements are also going to be the same, which is nothing but 1 volt. So I can say that I1 is nothing but 1 divided by 40 amps, because I1 is entering 40 ohms, the voltage across AB is 1 volt. Similarly, I2 is 1 divided by 20 amps. So what is I then? So I is equal to minus zero point 0.5 I1 plus I1 plus I2, as simplified from this equation. Now let me replace the value of I1 and I2 over here. So what I get over here is 0.5, and I1 is 1 by 40, plus what is I2? 1 by 20. So when I do this, I'm going to be able to replace this. 0.5 is nothing but half. So I'll get 1 by 80 plus 1 by 20. When I take the LCM as 80, this will be 1 and this will be 4. So what I get is 5 by 80 is the value of I. So now that I know this value, right, I know the value of I as 5 divided by 80. So the reciprocal of this, right, because it's 1 divided by 5 divided by 80, ultimately it becomes 80 divided by 5. So 5 and 1 and 6. So that means it is 16 ohms, right? So the RAB is the resistance looking in from the terminals AB, which is nothing but 16 ohms, which is nothing but the Thevenin's resistance. And that is what my load resistance should be in order to ensure that maximum power is transmitted from this network into the load RL, right? So my load resistance should be 16 ohms. So this is actually a gate question which was asked a few years back. So that's all with today's video. I hope you have understood the first case for maximum power transfer theorem, where the circuit is entirely resistive. There's one very important thing which needs to be understood here. Obtaining maximum power transfer for the load is not always acceptable or desirable, because when that happens, this circuit actually works at only 50% efficiency. Why is that? In order to find out, keep watching 11th hour. I'm sure you'll be able to get it when I discuss about it in the next video. Thanks for watching. Bye bye.